Alright, so this is chapter 11 on water for my BIOL105 students. And if you have your notes printed out in front of you, that's great. I'll help you guys fill those in as we go. Here are our learning objectives for this chapter. This is a great link if you want to calculate your water footprint. So it'll take you through how many showers you take, how many loads of laundry you do, how many dishes you wash, things like that. And it's really interesting to note that the average United States household uses about 2,200 gallons of water per day, which seems like a lot to me, doesn't it? So if you want, you can go to that calculator and calculate your own water footprint. This is a look at how water is disappearing. For example, this is Lake Chad in Africa. The area was much wetter 5,000 years ago, and I'll show you a picture of what it looked like. This huge lake has receded ever since then, and the lake has decreased over 90% since 1973 due to climate change, deforestation, and just human overuse, using the resources before they can be replenished. So this is a look. It is a lake on the edge, so you can see Lake Chad there in the center. The drainage basin, so that's where all it will receive water from, usually draining from mountaintops, is shown in green. And you can see how the lake is in the center there and the drainage basin surrounds it. Who owns the waters of Lake Chad? So these are showing pictures of the demands on the water. The human population surrounding Lake Chad has increased threefold over the past 3 years, probably for the resources that it provides. But the demands on the water are the grazing lands that surround the lake from animals, the irrigation needed to the farmlands, and you can see a picture there, and also others mine the lake for its mineral resources and its algae. This is showing Lake Chad over the course of 13 years. From 1973 to 1986, how the water is actually reduced by 84%, and then you can see how it continued on to be reduced even to present day. So again, just an example of showing how water is a resource, especially fresh water, that can be disappearing in certain areas. The global water budget, so over 70% of the Earth's surface is covered with water. There's equal amount of water evaporates as it precipitates, and that's what we call a cycle that we'll talk about. In your first part of your notes, it talks about the hydrologic cycle, and that's your first blank, is just the hydrologic cycle describes the distribution and flux of water through the Earth's ecosystem. Precipitation can have three fates. It can return to the atmosphere due to evapotranspiration. It can flow over the land as rivers and streams, or it can actually percolate, and that just means kind of run deeper down into the groundwater. So here's a look at how water covers over 70% of Earth's surface and how it's essential to all forms of life. So the geography of the hydrologic cycle, again, this is the first blank in your notes if you're following along and printed those out. The source of water varies by time and region. The oceans and near the coasts get roughly 100% of their rain comes from the ocean, and inland a great proportion comes from evapotranspiration. Especially in the Amazon, for example, 25 to 50% of the rain in the Amazon comes from evapotranspiration. You can see here on this slide how water in the atmosphere will condense and then fall to the earth. It'll fall on oceans, it can fall on ground as water and snow or ice. Then it can melt and become surface water. It can infiltrate the groundwater. Then the water in the oceans will go back up and evaporate. So this is just a look at the hydrologic cycle. The three phases of it are solid ice, liquid water, and gaseous vapor water, and that's just the evaporation. Water eventually returns to the atmosphere, collects on Earth's surface, and then moves underground, and that's the basic cycle. The residence time of water is the average time a water molecule will reside in that part of the cycle. It can vary widely, so in runoff, a water molecule will spend about 14 days in rivers, In groundwater, it can stay under the ground for hundreds, thousands of years. In the ocean, water can stay in the ocean for, again, thousands of years. Glaciers, it can stay there a long time because it'll be frozen as ice. But evaporated water over the ocean only stays about 9.5 days before it'll fall back to the earth as rain. This is a look at a cloudburst dropping a large volume of water onto Earth's surface in just a short period of time at a rate of about 4 inches per hour, which is an incredible amount of water. So this takes us to watersheds. This is your next blank, about halfway down your page and your first page of your notes. A watershed is a drainage basin is the area of land from which rainfall drains into a river or a lake. So it's also called a drainage basin. It can be separated by geological features like mountains or plateaus. Watersheds can be opened or closed. Open watersheds will eventually drain into the sea, and closed watersheds are inland basins that will not drain into the sea. This is a picture of deforestation and rainfall, showing the areas in brown are the loss of once extensive forests that have diminished the rainfall over large areas of Madagascar because less water can now evaporate back to the atmosphere from this landscape because water will evaporate from the leaves in those trees. So deforestation can actually cause less rainfall because water isn't being able to evaporate through the trees that don't exist anymore. This is a look at watersheds and how inputs and outputs can be measured. It's showing how the direction of the water flow will go depending on where the precipitation will fall. This is a look at the Rocky Mountains, showing how the different water basins are formed by topography. You can see the yellow lines are the peaks, and the water landing on either side of that yellow line will either flow east or west from the Rocky Mountains. Water is very essential to many ecosystem services, and these ecosystem services sustain life and support our environment. And this is the next part of your notes. You can fill in supporting services, which is where water is important for things like photosynthesis, the cycling of nutrient and carbon, and also on other biogeochemical cycles or food webs. So those are supporting services. Water is important for regulatory services. Rain and snow help to remove pollutants. Water helps to moderate temperature and also helps to keep the pH within normal range. And then water helps to provide provisioning services. And these are basic things like drinking water, providing seafood, providing water for agriculture and irrigation. This is a look at freshwater withdrawals, and these patterns of water withdrawals vary among different countries depending on the importance of industry and agriculture in their economies. So it's showing how different countries use different types of water for different uses. So whether they use it for industry, agriculture, or domestic or household needs. Where is Earth's fresh water? So out of the Earth's surface, 70% is water. 97.5% of that is salty water, meaning that's in the oceans. About 1.75% is frozen. 0.001% is in soil, and just about 1% of all of Earth's surface water, only 1% of it is fresh water. Fresh water is not evenly distributed, and we call the baseline water stress is a measure of the availability of fresh water relative to its demand, and it represents the total annual water withdrawals expressed as the percent of total annual flow in a region. So that's baseline water stress. This is a look at where is Earth's water. Most of Earth's water, as you can see there, is salt water in the oceans. And what isn't salt water, most of the fresh water is actually trapped in ice in the glaciers or the ice caps. Some of it is in the groundwater, and still, even less than 1% of it is found in rivers, swamps, marshes, and lakes. So fresh water, the percentage of fresh water that makes up Earth's entire surface is incredibly small. This is a look at the baseline water stress and how it varies per region. Areas with available fresh water and water withdrawal are coded as arid and low water use. So you can see here who's using more water than others throughout the world. So let's talk about groundwater. This is the next part of your notes. Groundwater is water that will reside in rocks and soil beneath the ground. This makes up about 0.3% of Earth's water. Most of it is in aquifers, which are layers of sediment and rock that are saturated with water. Aquifers can be incredibly large, so they're areas, again, below the Earth's surface. They're layers of sediment and rock saturated with water. They provide a variation of volume of water stored. Characteristics of groundwater, it can be from rain that does not evaporate or run off, so it'll percolate or sink through the rock to the water table. The water table is your first blink under characteristics of groundwater. The water table is the underground depth where your rock and your sediment are completely saturated with water, and that's called your water table. An aquifer is the saturated zone of water beneath the water table from which water can be extracted. So number 1 and 2 in your notes underneath characteristics of groundwater really tell you what a water table is and what an aquifer is. Then we talk about a recharge and discharge zone. A recharge zone can be an area from which water enters the water table from the surface, and a discharge zone is where groundwater will flow to the surface, where aquifers will meet the soil surface themselves. So this is a look at groundwater. It's showing how aquifers are regions of the saturated rock or sediment from which water can be pumped. Confined aquifers occur between relatively impermeable strata, so things cannot get through. And the water in confined aquifers may be under pressure, causing it to rise in wells above the level of the surface of the aquifer. And that's why we use wells, to get some of that water out of the aquifers. This is a look at showing Egypt. Rains that fell over 5,000 years ago created a huge aquifer that's below the Sahara Desert. And this aquifer is providing much needed water in this dry region, but accelerated use of this water could also deplete this non-renewable resource. Human uses and impacts of groundwater. We extract water through agriculture, industrial uses, and domestic uses. Some areas, extraction exceeds the recharge, and recharge again was just the ability for those aquifers to be filled back up. Primarily drinking water is a source for many, which is a big human use, and pollution can sometimes infiltrate groundwater if we have a faulty septic system or chemical storage tank leaks. We don't see septic systems a lot in LA because a lot of our water is pumped in by the city. But if you would live out in the country or out in the suburbs, you might have your own septic system where you're recleaning your own water use. And if we have a faulty septic system, a lot of that pollution can then seep it into the groundwater and pollute it. Obviously, if you have a chemical storage tank, if that were to leak, that could also leak chemicals into the groundwater. This is a look at how water is pumped up and out from the aquifer itself. And you can see how before pumping and after pumping, the level of water changes in the pump. When pumping ceases, the water table recovers, and the rate of recovery depends on the permeability of the aquifer, rocks, and sediments, how quickly more water can get down there. We talk about water, and you might think of too much water is floods. So too little water, water is a non-renewable resource, but too much water can cause floods. Flooding is a natural occurrence. There's seasonal volumes of rain or snow melt in many of those biomes we studied. And annual flood cycles can support rich agricultural areas. So when areas will flood, such as in the Nile or Mississippi, that actually causes nutrients to be dispersed in that flooded area and also water to be dispersed. This is a look at the Mississippi River floodplain where floodwaters will overflow into the floodplain of the Mississippi, which will enrich the soil with nutrients that are left behind in the river sediment. Too much water, we need to learn how to control floods though. In urban systems, this can be a challenge controlling floods. We know that living in LA because there's no way for the water to go. There's pavement all around us in big cities, and we call pavement and roofs and anything that does not absorb rainfall an impervious surface. So an impervious surface doesn't allow anything to get through it. Water can be channeled through storm drains to bodies of water. In our case, many of our storm drains lead to those concrete rivers that lead to the ocean. So that can help kind of drain too much water in the case of a flood. This is a look at landscape runoff and showing how the impervious surfaces of urban landscapes generate over 4 times as much runoff as do forests or meadows, which have completely pervious or permeable surfaces. So obviously we want some pervious surfaces, places where rainfall can be absorbed into the ground. Flooding frequency increases with urbanization in DC. This is showing how flooding frequency in the Anacostia River triples over time as urbanization overtakes DC. So this is just showing as urbanization increased, flooding increased, and that's because when it rained, water didn't have anywhere to seep into the ground. It came in contact with concrete, so there was nowhere for it to go. A little bit more about too much water. Growing paved areas and deforestation reduce flood control ecosystem service. A single tree in North Carolina can transpire or help evaporate 100 gallons per day. So some city solutions are increasing green space, using pervious pavement, which is pavement that allows for percolation or water to seep through, and creating what we call green roofs, which retain about 75% of water. Which are all great ideas. This is a look at a green roof on top of the Chicago City Hall. It can also keep summer roof temperatures a little bit cooler than the surrounding buildings. And engineers calculate that on hot days, Chicago temperatures would be as much as 77 degrees Celsius cooler if all downtown buildings actually had green roofs. So too little water. This brings us to our next point under 11.3 water distribution in your notes. Overdrawing surface water and overdrawing groundwater. So overdrawing surface water has to do with depleting and altering water bodies as water is diverging from lakes and streams. Overdrawing groundwater has to do with emptying aquifers, so the use of aquifers for agriculture and drinking water. This is a look at a sea near Uzbekistan. It's been rapidly shrinking since 2 countries began diverting water from the rivers that feed it in order to irrigate the crops. So instead of rivers feeding this water, the rivers are feeding irrigation. This is a look at the Colorado River. It originates in the Rocky Mountains. It flows almost 1,500 miles, and it supplies 7 states and 2 countries with water. There's many dams and untold diversions in it, which remove every drop of water from the river before it actually reaches the sea in the Gulf of California. So this is a look at how this river provides about 30 million people with water. Here's a look at the Ogallala Aquifer, and this is the largest aquifer in the world. It underlies 8 states in the Central Plains, so Nebraska, Kansas, Oklahoma, and Texas. It has been depleted by about 30% already, with an additional 39% loss projected by 2060. So subsidence and intrusion. Aquifer depletion results in loss of stored water, and subsidence, or the sinking of land above an aquifer that can create sinkholes. So subsidence is your first blank under subsidence and intrusion, and that's just the sinking of land above an aquifer. It can occur extremely slowly, um, or it can occur more quickly, in which case a sinkhole could develop. So subsidence is the first blank under number 1, and sinkhole is the second blank. This is a look at a sinking pole in San Joaquin, California. It's sinking extremely slow through the ground. Sinkholes, however, happen a lot more quickly due to aquifer depletion, and this is showing a house in Florida going through a sinkhole. That would be very scary to look at. Venice is sinking at about, I think, is it 2 millimeters per year? The Enchanting Canal of Venice is subsiding. The high water seen here most often occurs in the winter and affects the lowest parts of the city, such as this St. Mark's Square, as water moves in and out in response to the tides. Saltwater intrusion is your blank for number 2. Saltwater intrusion is the migration of salt water into freshwater aquifers. So if we overpump our aquifers in coastal areas, such as near the ocean, saltwater will actually migrate into those freshwater aquifers, which is not good. So this can be detected as early as 1854. This was happening in New York City, and this can be an issue all over the world. This is a video about saltwater intrusion. I'll let you guys watch this one on your own. and we'll continue on to water quality. So we'll look at water pollution and the effects of water pollution on ecosystems. Water pollution, the standards differ with use. It can be recreation versus a drinking supply in terms of how we pollute those water and what we're using it for. It's defined by physical, chemical, or biological. Physical pollution can be due to sediment or extra just physical things that could end up in it. Chemical pollution could be from industrial discharge, pharmaceuticals, or personal care products. And biological pollution could be from bacteria or other pathogens. These are parameters commonly measured in the assessments of water quality, and you can see the physical, chemical, and biological parameters included in the assessment here on water quality. Bioassessment uses organisms living in the water as an indicator of quality. So it'll look at the vegetation, the fish, the insects, the invertebrate, and the mussels, and it'll pay special attention to those sensitive to water. And if these biological species are surviving, then that usually means the water's okay. But if any sort of these species are dying off, they probably means that something's wrong with the pollution in the water. This is a look at sources of water pollution. Storm water runoffs from streets and other impervious surfaces is an example of non-point source pollution, and chemical-laden water released from industrial facilities, like in the picture on the bottom, is an example of point source pollution. The effects of water pollution on ecosystems. So we're going to go through streams, lakes, estuaries, and oceans. And you guys can write in your own notes here. I don't leave you too much space. Streams, if streams get polluted, this can devastate the biodiversity. It'll make filter feeders really vulnerable. And again, those are any sort of living organism that takes in all the water at one time and filter feeds it through its teeth. Greater than 50% of U.S. native freshwater mussels are endangered or extinct due to stream pollution. Heavy metal, the pH can be altered from mines. Lakes can be affected by water pollution. Nutrients can accumulate from runoff. Eutrophication is what we call the enrichment of bodies of water with excess nutrients. And eutrophication of water with excess nutrients can result in rapid growth of certain populations of algae. And if we get algae, what they call those algal blooms, if we have too much algae in the food web, they can block out sunlight from getting to the fish that feed off of them below them. So algae blooms due to eutrophication is not good. Large amounts of this organic material can use up oxygen and can reduce the biodiversity. Estuaries are usually found at the base of watersheds where many pollutants can enter them. Excess nitrogen and phosphorus can cause eutrophication, so a buildup of too many nutrients, which could create too much bioaccumulation of algae, leading to a dead zone where the oxygen is so low that few organisms can actually survive in it. Oceans, then, we call dead zones a zone in the ocean where bacteria decomposes organic matter and depleting the oxygen dissolved in the surrounding ocean water. So we call that the dead zone in the ocean. The United Nations estimates there's over 200 dead zones in the oceans, and they're all associated with the mouth of a river, so where a river would bring in pollutants to the ocean. It's a major contributor to the decline of many fish species. Nutrient pollution in the ocean can also harm coral reefs, and mercury bioaccumulation can occur in large fish. And then we talk about oil, where spills and discharge from oil fields can also damage the ocean. The blank at the top of your third page of notes is referring to ocean acidification, which we'll get to in a slide or two. So ocean acidification is a reduction in ocean pH due to increased carbon dioxide input from the atmosphere, which also threatens to alter the ocean ecosystem. So this is a look at dead zones. And again, a dead zone is an area where little to no oxygen is present, which will harm the organisms in the water. And normally dead zones are found near where bodies of water or rivers or streams empty out into oceans because they are bringing a lot of unnecessary nutrients or pollution to the water there. So here is ocean acidification. This is a reduction of pH of the oceans due to carbon dioxide input. 25% of carbon dioxide in the atmosphere is naturally absorbed by the ocean, and these acid can actually calcify many organisms. It can slow coral growth. It can be the loss of calcareous species. This is a look at what ocean acidification can do to a sea urchin, which is a picture on the right. Sea urchins can lose their ability to fully form their spines when raised in conditions with high levels of carbon dioxide. Finally, each year, millions of tons of trash, anything from fishing gear to plastic grocery bags, make their way into the oceans. Winds and currents have concentrated nearly 4 million tons of this garbage in an area measuring 1.2 million square kilometers. This area is about halfway between North America and Hawaii, and it has come to be known as the Great Pacific Garbage Dump. Chemicals can leach out of the plastics. They can alter birds, fish, marine mammals. So we call this area the Great Pacific Garbage Dump, where all this trash kind of congregates due to wind and ocean currents. Here's ocean garbage. Tens of thousands of tons of trash, such as fishing nets, plastic bags, end up in the ocean. And the maps show where most large ocean trash is found, and it's highlighting that kind of North Pacific between North America and Asia, that area where most of this trash would congregate due to the ocean wind currents. These are the countries that pollute the oceans the most. So surprisingly, what you might not realize is the United States is actually pretty low, which, I mean, we don't want to pollute our oceans at all, but the big ones, China, Indonesia, Philippines, Vietnam, are most likely producing the most just junk into the oceans because they're the ones that really produce the majority of products that we own. I'm sure most of the products in our home are either made in China, Indonesia, Philippines, or Vietnam, especially if we count all our clothes too. But still, not something we ever want to contribute. Water management and conservation. 700 million people live with water scarcity. There's more than 3 times that many lack the access to clean water. Most of this does happen in poor developing countries, but wealthy nations can also face water shortages, and it's estimated that there will be a 50% increase in water use by 2050. So we're looking at ways to how to manage and conserve water more effectively. They say water is everywhere, but 10% of Earth's people do not have enough water, and nearly 40% must drink and bathe in water that does not meet even the most minimal standards of sanitation. And we already learned without sanitation and clean water, diseases spread. Ebola is an example of that, and other things can happen without sanitation. And that starts with water. So how do we regulate the flow? In this part, humans have modified streams in order to minimize the risks of both floods and water shortages. And I leave you guys to space in the notes to write your own notes as we go through this. Dams control floods, store water, and generate electricity. The U.S. has almost 80,000 dams that are higher than 7 meters. They change the ecosystem, they alter the animal movement, the flow downstream, and the seasonal water flow, but they also provide some electricity and the ability to store water and control flooding. Here's a look at the Hoover Dam, which sits at the boundary of Arizona and Nevada on the Colorado River. It Created by Lake Mead, it's the largest reservoir in the United States. Sediment collects behind the dam in Lake Mead, but very little flows downstream to replenish sandbars and ripen habitats that animals might need. Channelization and artificial levees prevent flooding, control flow of water. They provide floodplains for agriculture and urban development. They protect adjacent land but speed flow of water, and they increase flood potential downstream. This is a look what channelization looks like. This segment of the Kissimmee River in Florida is shown before and after channelization. So you can see in letter A, the picture on the left, that's the normal flowing channel of the river. But in effort to restore the floodplain and improve aquatic habitat, you can see how a channel was formed that goes straight through and kind of takes away that meandering of the river. Levee failure following Hurricane Katrina. So this was a big thing that was bad about Hurricane Katrina. The water poured into the below sea level basin of New Orleans, flooding about 75% of the water area, or the metro area. High water marks ranged from 13 to 18 feet along the Mississippi flood wall. So these were levees that failed during Hurricane Katrina. Wetland loss and restoration. One of the most important lessons learned from Hurricane Katrina is how critical wetlands are in helping to mitigate the effects of flooding. Over the past 200 years, the total area of wetlands in the lower 48 United States has been reduced from 90 million to 40 million, and a large part of that has been along the coast. Much of the remaining wetland has been degraded by drainage, changes in water supply, and vegetation damage. Drainage can result in significant changes in vegetation cover and accelerate the decomposition of peat. And it can also make wetlands vulnerable to destructive fires. Here's a look at wetland loss. It's occurred during the past 2 centuries, but the rate that loss was slowed by the passage of the Clean Water Act, which included provisions for wetland protection. And in even recent years, restoration efforts have been gradually increasing or stabilizing the wetland areas. Wetland restoration, many countries set policies to stop their loss. The U.S. doesn't necessarily have a net loss policy. If wetland is destroyed or impaired through development, equal amounts must be restored or protected. And there's many wetland projects and restoration projects underway. Here's a look at wetland restoration. It was formerly drained and degraded, but now this 60-acre marsh near Seal Beach, California, sound familiar? Has been restored and once again provides important ecosystem services. Then just brings us to the last part of our notes with estuarine wetland loss. Estuaries are at a risk through alteration of water flow of feeding rivers. So dams and diversion have altered seasonal water flow. So the fresh water entering the estuary can be reduced, which increases the salinity or the saltwater content. Here's a look at estuarine wetland loss. Destruction of most of the tidal wetlands in San Francisco Bay, shown in red, is a major factor contributing to the diminished water quality in this large estuary, taken starting in 1848 and then taken today. Okay, so crop irrigation has to do with conservation and management because many irrigate their crops. 70% of fresh water irrigates crops. Irrigation efficiency is under your notes under number 3, under managing and conserving water used in agriculture. And irrigation efficiency refers to the percentage of the water applied to fields that is actually used by crops or plants. Most farms are less than 40% efficient, and simple changes in practice can help decrease the use by 15% to 50%. Over 60% of the water applied by flood irrigation to this Arizona cornfield will simply run off or evaporate without being used by the plants in the top picture. But in drip irrigation, shown in the bottom picture, by comparison, The feeds is minimal, it's efficient, and the amount of water is put directly where it's needed in this California vineyard. So looking to the top picture versus the bottom picture, most of the water in the top picture will just evaporate without even being used by the plants. But in drip irrigation, shown in the bottom picture, the water will go directly to the plants that it needs. Water reuse. This can conserve water and provide benefits when water is reused. Municipal wastewater treatment centers are helpful for reusing and treating irrigation water, which will reduce the need for water. It will reuse water that has residual nutrients and reduce fertilizer needs. So this is a look at the Orange County Water District. Will purify wastewater for release into the groundwater basin in Fountain Valley, California. It takes highly treated wastewater and purifies it through a 3-step process of microfiltration, reverse osmosis, and treatment with ultraviolet light. So this is where we get to desalination. So we're on the last page of your sheets of notes. Desalination is converting to seawater to fresh water. So that's the process of removing salts and other chemicals. That's desalination. It's extremely expensive. The two main methods of desalination are distillation, which is boiling water and condensing it to steam, and reverse osmosis, which is filtering water through a selective membrane. So those take you through the first 3 blanks on the top of your last page. It's very expensive. It costs energy, time. It's cost effective in some regions. But for the most part, desalination is extremely expensive. Desalination and energy, this is in the United Arab Emirates. It generates electricity from natural gas through a desalination plant. The heat from the natural gas turbines is used to desalinate seawater by distillation. Water pricing. Changing water pricing may enhance sustainable conservation. By removing subsidies for farmers, it could encourage them to try other conservation measures like drip irrigation or irrigation improvements. And residential rates are also effective, giving people a flat rate versus a metered rate in homes. Municipal wastewater treatment. It's historically sewage was dumped into the waterways, and again, this is incredibly problematic in high population areas. In Latin America, still only 15% of sewage is treated. So in Latin America, you see high rates of waterborne illnesses. In the United States, most of our cities and towns treat sewage, and they treat sewage through what we call municipal sewage treatwater plants, and we abbreviate those MSTPs. And this is a stepwise process that removes wastes and some chemicals. This stepwise process has different treatments, and the pre-treatment wastewater that has first had large soils removed, such as rags and gravel, flows into tanks where it then undergoes primary treatment, and this allows particles to settle out, forming a sediment called sludge. Secondary treatment allows bacteria and other microorganisms to break down organic matter dissolved in wastewater. And the advanced treatment, or tertiary treatment, then is what you could put advanced or tertiary treatment for that last blank, is used to remove inorganic nutrients from the water. So this is a look at wastewater treatment. The pre-treatment takes out the big stuff, the primary treatment creates the sludge, and then secondary and advanced or tertiary treatment of the wastewater before it'll be kind of pumped back into the ground. Your neighborhood municipal sewage treatment plant. Communities use different components of wastewater treatment depending on their needs. This is an aerial view of a wastewater treatment plant in Portland, Maine, showing primary and secondary treatment. On-site wastewater treatment, an example of this is a septic system, and that's your blank under number 1. Households rely on septic systems to treat their water and sewage. It's typically found in less densely populated areas. The sewage settles in an underground tank, and microorganisms break it down. And then the leach field is the area where the wastewater is discharged in the soil and microorganisms continue to leak to break down the wastewater. So leach field is your last blank under your notes. This is a look at how a septic system is run. And you can see here the tank and then how it drains the water into the leach field where microorganisms will break the water down. So we'll finish with water and you. In the United States, 13% of fresh water is used in municipal systems. Bathrooms and your laundry use the highest proportion. Toilets, washing machines, showers are the biggest users. So as you're looking to decrease your water use, think about how many times you flush your toilet, wash clothes, how long you take a shower. Leaks can account for 14% of household water. So actually just water leaking from your pipes that you might not know about is losing water. And in the United States and Canada, city water systems can lose 10 to 30% just by leaks, and it can be higher globally. And that can be a huge cost. How do we use our water? This is just how Americans use water in the bathroom, with more than 61% supplying toilets, showers, faucets, and baths. Fixing leaks and updating water fixtures can significantly reduce water use in the home. Water efficiency, you can reduce your water consumption. There have been technology advances used. The government has offered incentives through their Water Sense program, which has helped improve water efficiency, providing low flow toilets and shower heads that also use less water. So this is a part of the EPA Water Sense program, creating shower heads that use a lower flow of water. So you can use less water, be more sufficient, shorter showers, turn the faucet off while you brush your teeth. You can use rain barrels or cisterns to collect rainwater. Saving water at home, more ways you can use water at home. If you guys learn anything from this course, it's just to get a better idea and a better awareness of the environment around you and how you can just be a better steward of the environment that we've been given. How much water do you use? You can actually look up to see how much water you use. The average American uses 300 to 378 liters of water per day, but it's been determined that you only need 8.7 liters per day to survive. The World Health Organization says you need 50 liters per day for basic human needs. So if you guys you can track how much water you use during the next 24 hours, and then what conservation measures you could take and how much water you could actually live with. And we'll end with that.